PostgreSQL is widely celebrated as the world's most advanced open-source database, powering everything from startups to global enterprises. But beneath its robust reputation lie hidden pitfalls that can catch even the most experienced teams off guard. Today, we'll uncover the critical problems that often go unmentioned until it's too late. Whether you're running millions of requests daily or just starting out, understanding these risks is essential for keeping your data safe and your systems running smoothly. Let's dive into the real-world issues that every PostgreSQL user should know before disaster strikes. First up is the silent database killer, transaction ID wraparound. PostgreSQL uses a 32-bit transaction ID for its multi-version concurrency control. With about 4 billion IDs, it sounds like plenty, but in high-traffic systems, you can burn through these much faster than expected. When the counter nears its limit, PostgreSQL enters emergency mode and can even shut down to prevent data loss. This can happen suddenly, especially if vacuum processes are disabled during maintenance. Monitoring transaction age and keeping auto vacuum running are your best defenses against this hidden threat. Let's break down the transaction flow. Every new transaction is assigned an XID, then executed and committed. The XID counter wraps around after 4 billion, and the vacuum process is responsible for freezing old XIDs to prevent wraparound. If vacuuming is delayed or disabled, your database risks going read-only or even shutting down. Regularly monitoring transaction age and vacuum activity is crucial to avoid this scenario. Most teams start with asynchronous replication because it's simple and fast. But here's the catch. If the primary server fails, any transactions not yet replicated are lost forever. This isn't just theory. Real companies have lost seconds of critical data during unplanned failovers. Synchronous replication can prevent this, but it comes at the cost of increased latency. Understanding your replication mode and its trade-offs is vital for data integrity. In asynchronous mode, the primary sends data to the standby, and the client gets an immediate acknowledgement. But if the primary fails before the standby catches up, data is lost. In synchronous mode, the primary waits for the standby to confirm receipt before acknowledging the client, ensuring no data loss but increasing commit latency. The choice between speed and safety is a balancing act every team must consider. PostgreSQL's physical replication copies entire disk blocks, not just logical changes. This means operations like index rebuilds or bulk updates can generate massive amounts of write-ahead log, WAL traffic. If a block is corrupted on the primary, that corruption is instantly replicated to all standbys. Monitoring WAL generation and understanding its impact is crucial, especially during maintenance or heavy write operations. PostgreSQL's multi-version concurrency control, MVCC, creates a new row version for every update, leaving old versions until vacuumed. In high update environments, this can cause tables to balloon in size, sometimes by orders of magnitude. If vacuum can't keep up, storage usage spirals out of control. Monitoring table bloat and tuning vacuum settings are essential for keeping your database lean and efficient. Let's visualize how unchecked updates can inflate table size. In one real-world case, a 10 gigabytes table grew to 280 gigabytes in just 3 months due to constant updates and slow vacuuming. The pattern is clear. Without proper maintenance, your storage needs can quickly outpace your actual data volume. Regularly check for bloat and adjust vacuum settings to match your workload. PostgreSQL's connection model spawns a full operating system process for each client connection. This was fine in the past, but with modern microservices, hundreds or thousands of connections can overwhelm the server. As connections increase, throughput drops dramatically due to context switching and lock contention. Connection pooling tools like PG Bouncer help, but the underlying model remains a bottleneck. Unlike clustered index databases, PostgreSQL stores table data in heaps. Every primary key lookup requires 2 I divided by O operations. First, an index lookup to find the row location, then a heap lookup to fetch the actual data. This doubles the I divided by O cost and adds storage overhead, especially with large composite keys. Understanding this tax is important when designing tables and indexes for performance. PostgreSQL's on-disk format changes between major versions, making upgrades a challenge. Tools like PG Upgrade can minimize downtime, especially with the link option, but require careful planning and both versions on the same file system. Logical replication offers near-zero downtime upgrades but comes with its own limitations, such as manual sequence, synchronization, and schema coordination. Setting up streaming replication in PostgreSQL looks easy in tutorials, but production reality is much more complex. Multiple configuration files, replication slots, and careful coordination are required. Missing a single setting can break replication, often discovered during a crisis. Replication slots are now essential to prevent wall file deletion before standbys catch up. PostgreSQL's query planner makes decisions without user hints, sometimes choosing suboptimal plans. For example, it may pick a sequential scan when an index scan would be faster. You can adjust global cost parameters or rewrite queries, but direct hints aren't part of core PostgreSQL. Extensions exist, but they add complexity and aren't always available. While PostgreSQL 14 Plus added compression for large values, regular rows remain uncompressed. For tables with hundreds of millions of small rows, this means no compression benefit and significant storage overhead. Competing databases compress blocks of rows together, saving space. Understanding these limitations helps you plan for storage growth and choose the right database for your needs. Despite these challenges, PostgreSQL remains a powerful and reliable database if you know what to watch for. Proactive monitoring, careful configuration, and understanding the architecture are key to avoiding late-night surprises. Plan for connection, pooling, monitor transaction age, use replication slots, and budget for more storage than your raw data size suggests. With the right strategies, you can harness PostgreSQL's strengths while sidestepping its most dangerous pitfalls.